Hi everyone, I am Dr. G. Nagaraju, Assistant Professor in the Department of CSC, AML, IoT and RAI, VNR, VJET. Now I will discuss about the one of the data structure concept that is called as a trees. Now we have two types of data structures are there. One is called as a linear data structure and another one is called as a non-linear data structure. And the present topic trees comes under non-linear data structures. The nonlinear data structure are used to represent the hierarchical relationships between the grandfather and his children and so on. The definition of a tree is a tree, it can be defined as a finite set of one or more data items such that there is a special node called root of the tree and the remaining nodes are partitioned into the disjoint subsets, each of which represents a tree. So this is the definition of a tree. Now the tree terminologies are now in the tree we discuss or here we are calling it as one node as a root node. So the definition of a root node is the root node is the topmost node in the tree. So here in the given diagram, A is called as a root node. So it is the topmost node in the tree. Suppose if R is equal to null, then that means here now the tree is empty. The second one is subtrees. If the root node R is not null, then the trees T1, T2, T3 are called as a subtrees of R. So in the diagram here, so from here to here, so this is called as a left subtree. Again here this is called as a right subtree. Again here in that one, in that left subtree, again here this one which represents the left subtree and so on. So these all are comes under the subtrees concept. Leaf node. The definition of leaf node is a node that has no children is called as a leaf node. So in the given picture, the nodes like K, L, M, N, O, P, G are called as a leaf nodes because here there are no children for these nodes. So that's why here these nodes are called as a leaf nodes. Path. Path means here a sequence of consecutive edges is called a path. So here there is a path from A to K. So that is from A to B, B to D, D to H and H to K. Again there is a path from A to P, A to C, C to F, F to J, again J to P. This is called as a path. Next, ancestor node. An ancestor of a node is an predecessor node on the path from root node to that node. Then the root node does not have any ancestors. If the in the given tree here the nodes A, C, F are the ancestors of J. Next one is the descendant node. A descendant node is any successor node on any path from node to that leaf node. And leaf nodes do not have any descendants. In the given tree here the C, F, J, O are the descendants of here node A. Then degree. Degree of a node is equal to here the number of children that a node has. The degree of the leaf node is 0. And in the degree again for the directed, so we can calculate the degree for directed trees. Again here the undirected trees. Suppose if the tree it is not a directed tree, then we have the in degree and the out degree. The definition of in degree is in degree of a node is the number of edges arriving at that node, that is called as a in degree, and the out degree of a node is the number of edges leaving that node, that is called as a out degree, and this in degree and out degree is there for the directed tree. So here suppose if the tree is like this, A, B, let us assume C, D, E, F, from there is here A to D and D to A to B, again here B to C, D to E and D to F. Now this is the given directed tree. Now in this case here the in degree of A is here 0 because there are here there are the number of edges arriving to this node A is 0. Again here for this B, the in degree means here the incoming edges are 1. So the in degree of here this B is 1. And similarly here the out degree means here the edges that are leaving from that node. Okay, so there is a here one edge that is leaving from that B is here, from B to C is there. So here the out degree is 1. And here coming to here the C, now for the C here the in degree is 1 and out degree is equal to 0. There are no outgoing edges. And similarly here for this D, now the in degree is 1 and the out degree is 2. Okay, so in that way we can calculate the in degree and out degree for each node in the given tree. So for E, the in degree is 1 and the out degree is 0. And for node F also, the in degree is 1 and the out degree is 0. Next, we have different types of trees are there. They are called as a general trees, forests, binary trees, binary search trees, expression trees, and the tournament trees. Now, coming to here, the binary trees. A binary tree is a tree in which no node can have more than 2 children. Typically, these children are described as left children and the right children of that parent node. Now, the definition of a binary tree is a binary tree T is defined as a finite set of elements called nodes such that T is empty, means T has no nodes, called the null tree or empty tree. T contains a special node or that is called as a root node of the tree T, and the remaining nodes of the tree T form an ordered pair of disjoint binary trees T1 and T2, each of which represents a binary tree. So in simple term here, the binary tree contains at most 2 children. So that type of tree is called as a binary tree. So a binary tree which do not contain more than 2 children. So parent node. So in the given tree here, the parent node of here this 2 and 3 is 1. So parent node of 2 and parent of 3. So parent node of 2 and parent node of 3 is 1. Okay, so if n is any node in T, so here the T which is nothing but a tree. So in this case it is a binary tree that has a left successor S1 and the right successor S2. Then n is called as a parent of here that S1 and S2. So level number, so every node in the binary tree is assigned a level number. The root node is defined to be at level 0. The left and the right child of that root node has the level number 1 and so on. So already I have explained about the degree of a node, which is equal to the number of children. Okay, suppose if it is a undirected tree, the number of children that represents the degree of a node. So degree of a leaf node is 0 because here there are no descendants for that leaf node. Leaf node has 0 children. So that's why the degree of a leaf node is 0. Next one, siblings. All nodes are at the same level and share the same parent are called as a siblings. Okay, so here these 2 and 3 are called as the siblings because here the 2 and 3 are having the same parent which is nothing but 1. And similarly 4 and 5 are called as the siblings because they are having the same parent which is nothing but 2. 6 and 7 are called as a siblings. 8 and 9 are called as a siblings. 10 and 11 are called as the siblings. So this is the definition of a sibling. Then a path, a sequence of consecutive edges is called as a path. So in the given figure, there is a path from 1 to 2, 2 to 4 and 4 to 8. So this is the path. The definition of a depth is the depth of a node n is given as the length of the path from the root R to the node n. The depth of the root node is 0. And next one is the height. Height of a tree is the total number of nodes on the path from the root node to the deepest node in the tree. A tree with only a root node has the height of 1. A binary tree of height h has at least h nodes and at most 2 power h minus 1 nodes. Then the full binary tree and complete binary tree. So in the full binary tree, each node contains either 0 or 2 children. Then that type of tree is called as a full binary tree. So here in the given tree, this node contains two children. Again here let us assume this is A, B, C, D, E, D, E, F, G. Now A has two children, again B has two children, C has zero children, E has two children, F has zero children, G has zero children, again D has zero children. So that according to the definition of a full binary tree, each node contains either zero or two children. So this is the example of a full binary tree. And complete binary tree, so in the complete binary tree, so except the last level, so the remaining levels are completely filled and last level are filled from left to right, then the type of tree is called as a complete binary tree. So now here this one, it is the last level. So before the last level, okay, before the last level it is completely filled and last level elements are filled from left to right, okay, then that type of tree is called as a complete binary tree. So the complete binary tree, we can represent this complete binary tree by using here this arrays. The best data structure to represent this complete binary tree is using arrays. So representation of binary trees. So there are two ways to represent a binary tree, and one is using arrays and the other one is using the linked lists. So here in the diagram here that shows the two representations. So here the first one that represents the linked list representation, and here this one it represents the array representation. Suppose here this is a given tree A, B, C, D, E, F. Okay, now the array representation is here. Now A array, that is at the first position A, and the left child, A's left child is at in the first position, again A right child is at the second position. Okay, so let us assume 0, 1, 2. Then here the D is at after that C, we can place after D, here we have to put the D. Again here there are no childs for here this C, so that here this position is empty. Okay, so leave that position, then after that write that G. So in sixth position here we have G is there, this is G. So this type of representation is called as the array representation. Suppose if the parent is at the first position, okay, if the parent is the first position, then its left child is at the suppose if the parent is at the nth position, then the left child is at the 2n plus 1 position, okay, and the right child is at the 2n plus 2 position. Suppose here now that n, which is nothing but 1, if the parent is at the first position, then its left child is at the 2 into 1 plus 1, means here that left child is at the third position. And similarly here the right child is at the 2n plus 2 position, that is nothing but, so 2 into 1 plus 2 means here the right child is at the fourth position. Okay, so this is applied to here all the nodes including the root node. If the root node is at the 0th position, then we get the left child is at the 2n plus 1 position. So here the n value is equal to 0, so that the left child is at the first position. And similarly the root node, the right child is at the second position. Similarly here we can get the right child by using the equation 2n plus 2. So here n is equal to 0, so that the right child is at the second position. And in the similar way we can calculate here the left child position and the right child position in the given array. And suppose we can find the parent of a node, we can find the parent of a node by using here the equation. Suppose here the left child is at the suppose this is n position, or here the third position, okay, so that here the parent is at the first position. And similarly here now the right child is at the fourth position here. Now its parent is at the first position, okay. And better here and by using here this indexes, okay, we will get here this equation. Suppose here if the array is starting from the first position, if the array starts from the first position, if the array index is starting from the first position, so let us assume 1 2 3 4 5 6 7 8 9 10, okay. And here let us assume here the array index is from first position 1 2 3 4 5. Let us assume here the 6 is empty and 7. So in the first position we have A is there, in the second position we have B is there, in the third position we have C is there, in the fourth position we have D is there, in the fifth position we have E is there, sixth is empty, and in the seventh position we have G is there. Okay, so by using here this representation we can get the parent node. Okay, suppose here the B and C, so B and C parent is here this A. Suppose here if the child is at the nth position, we can get its parent node position by using the equation n by 2. Okay, if the child is at the nth position, then we can get the parent position by using the equation n by 2. So here now the B parent is A, similarly C parent is also A. We can get the B parent by using here this index 2. So here the n value is equal to 2. We get 2 by 2, we get 1, means whatever node, whatever value is there in the first position, that is nothing but the parent of B. And similarly here we can get the parent of C. So parent of C is also A. So here the n value is 3. So 3 divided by 2. Okay, we can get here this is integer division by integer division. We can always get the integer. Okay, we cannot get that fractional part like 1.5 etc. So 3 by 2 means here 1. So whatever node is at the first position, that is nothing but the parent of here that 1. Okay, and similarly here now G, now we want to find here the parent of G. Now the G is at the 7th position, so 7 divided by 2 we get 3. So whatever value is at the third position, that is nothing but parent of G. So in this way here we can calculate the parent of node. So this type of representation is called as a array representation. And similarly here the another representation is the linked list representation. So in the linked list representation, each node contains 3 fields, and one field which is used to represent the data, and the remaining fields are used to pointing to here the left children and the right children of that node. Now this is the linked list representation. Now in that linked list representation we have nodes are there. Now in this one here the node contains 3 fields. So one field which is used to represents the data, and the remaining 2 fields are the pointers which are pointing to here the left subtree as well as the right subtree. So here the we can represent here this node in C by using the structures. So that is nothing but here the struct node. We can take here, it has 3 fields are there. So one field which is used to represents the data, so that we can write integer data, and the remaining 2 fields are the pointers which are pointing to here the left child as well as the right child, so that we can write struct node star right child and struct node star left child. Okay, so in this way here we can represent the, now this is the C node structure syntax to represent the here the node of a tree. Okay, now here this is a tree representation. Now this A which contains 2 children, one is the left child B and the other one is the right child C. Okay, so left pointer is pointing to B and the right pointer is pointing to C. Okay, so again B contains 2 children. Okay, left children is D, again the right children is E. Again C has only one child which is nothing but this is F. Okay, so C has only one right child is there, that is F, and C do not have the left children, so here this value is null. Again here D do not contain or do not have the left and right children, so here these values are null. These are null. So in this way we can represent the tree using linked list. So already I have explained these equations, how to get that left children, again right children, and the parent of a node. This is also linked list representation. Next to coming to here the one of the special tree that we are calling it as a binary search tree. So binary search tree, it is a binary tree, means which contains at most 2 children. But the property of the binary search tree is the left child value is less than the parent node and the right child value is greater than the parent node. Then that type of binary tree is called as a binary search tree. See here in the given diagram. Now 8 it is a root of the node. Okay. Now here the 3, the left child values are less than here this 8, and the right child values are greater than this 8. Okay, so anyway the left child value is 3 which is less than 8, and the right child value is 10 which is greater than 8. And coming to here this 3, okay, now the 3 left child value is less than 3 which is 1, and the right child value is greater than 3, so it is nothing but 6. It is satisfying here that binary search tree property. And here coming to here the 6, the left children value is 4 which is less than 6, and the right children value is greater than 6. Okay, that is nothing but 7. And coming to here this 10, again here there is no left children, and the right children value is greater than here this 10. Okay, which is nothing but 14. The 14 contains only one children, that is the left children, so always the left children value is less than here this 14, so which is nothing but 13. So in the binary search tree, each node satisfy here that binary search tree property, that is the left child value is less than the parent node and the right child value is greater than the parent node, then that type of tree is called as a binary search tree. Now we have expression tree is there. Now in the expression tree, the intermediate nodes, okay, these are the intermediate nodes. The intermediate nodes are used to represent the operators, and the leaf nodes means here the nodes which do not have any children, that nodes are called as a leaf nodes. Okay, that leaf nodes are used to represent the operands. Okay, so here that leaf nodes are either the numerical values, or in some cases here they are the alphabetic values, like here A, B, C, etc. So this type of tree is called as a expression tree. So here this one, it is the example for 3 plus 5 plus 9 into 2. So these are the some of the examples of expression trees. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.